Let us find intercepts, the x and y intercepts, zeros, and asymptotes of rational functions. Before that, let us first define what a rational function is. A rational function is a function which can be written as the ratio of two polynomial functions. That is, f of x is equal to the numerator is a polynomial function while the denominator is a polynomial function, and the denominator or the function in the denominator should not be equal to 0. Why? Because if the denominator is equal to 0, then our function will be undefined. Thus, it is important that our denominator should not be equal to 0. In finding for the x and y intercepts of a rational function, let us remember that the x-intercepts of a rational function are the zeros of the function. What does it mean? When you say zeros of the function, those are the values of x which will make our function equal to 0. And to do that, we let f of x equal to 0 and we solve for the values of x. Then we will get the x-intercepts. The zeros of a function are values that will make our function equal to 0. While to find the y-intercepts, we let x equal to 0. Let us have this example. Find the zeros and intercepts of f of x is equal to 2 over 3x. Is this a rational function? Yes, it is. Now, the zeros are none. The x-intercepts are none, while the y-intercepts are none. There are no zeros, there are no x-intercepts, and there are no y-intercepts in this kind of rational function. Why? As you can see, if we solve for the zeros, we are also solving for the x-intercepts. And when we solve for the x-intercepts, we let y equal to 0. This is our y or f of x. We can use them interchangeably. But if we refer to a function, we use f of x. Now, if f of x is 0, and 0 by cross multiplication, 0 times 3x is 0, is equal to 2. Well, it does not mean anything. It is undefined. In that case, we cannot solve for a value of our 0 or x-intercept. Thus, this rational function has no zeros. Since it has no zeros, then it does not also have x-intercepts. What does it mean if our function does not have an x-intercept? It means that the graph of our rational function will never touch or cross the x-axis, because x-intercepts are the points wherein our graph will touch or cross the x-axis. Now, to solve for the y-intercepts, we will let x equal to 0. In this case, if we have 3 times 0, it will become 0, and we have 2 over 0. This is undefined. We cannot divide anything by 0. If that is the case, we cannot solve it. It is undefined. Thus, we do not have a y-intercept also. What does it mean? It also means that the graph of this rational function does not cross or touch the y-axis because it has no y-intercept. That is how are we going to solve for the x and y-intercepts of our rational functions. Let us talk about asymptotes of a rational function. An asymptote is a straight line which a curve approaches arbitrarily closely as it goes to infinity. Again, when we talk about asymptote, we are talking about lines. That means it is an equation. It is not a point or a value of x or y. It is an equation. Now, an asymptote is a line wherein our graph approaches as close as possible, but it never touches or crosses that line. That is an asymptote. Remember that a rational function can have at most one horizontal or oblique asymptote. What does it mean? At most is less than or equal to. That means it could have one horizontal or oblique asymptote or zero or none. It does not have a horizontal asymptote. When we talk about oblique asymptote, it is neither horizontal nor vertical. It is a slant. It is sometimes referred to as slant asymptote. However, our rational function can have many possible vertical asymptotes. Vertical lines that our graph approaches as close as possible but never touches. The vertical asymptotes are obtained by setting the denominator equal to 0 and solving for x. Again, to determine the equation of our vertical asymptote, we'll let our denominator equal to 0 and we solve for x. Solving for x here is not intended to look for the value of x, but to look for the equation of the vertical asymptotes. There will be a vertical asymptote for each 0 of the denominator that is not a 0 of the numerator. How about horizontal asymptotes? When we talk about horizontal asymptotes, we will refer to the degree of the numerator and the degree of the denominator. Again, when we are talking about functions, we have this term called degree, which refers to the highest exponent of the variable in the numerator and the denominator. Now, we refer to the degree in the numerator as n and the degree of the denominator as m. Remember that if n is greater than m, what does it mean? That when the numerator or the degree of the numerator is greater than the degree in the denominator, there is no horizontal asymptote. But there is an exemption. If the degree of the numerator is exactly 1 more than the degree of the denominator, then there exists a slant or oblique asymptote. When does an oblique asymptote occur? When the degree of the numerator is exactly 1 more than the degree of the denominator. Next, if the degree of the numerator is less than the degree of the denominator, then the x-axis and the equation is y equals 0 is a horizontal asymptote. Next is, what if the degree of the numerator is equal to the degree of the denominator? Now, if that is the case, we have a horizontal asymptote that the equation is, this is the equation, y is equal to the leading coefficient of p of x here refers to the numerator function, and the leading coefficient of q of x, which is the denominator function. Recall what a leading coefficient is. It is the coefficient of the leading term. The leading term is the term that contains the highest exponent of the variable. Okay? Let us have this example. Find the asymptotes of the function f of x is equal to x plus 10 all over x minus 5. Again, x plus 10 is a polynomial function and x minus 5 is a polynomial function. Then this is a rational function. Now, first we will look for the vertical asymptotes. Again, to determine the vertical asymptotes, we simply equate our denominator, this is x minus 5, equal to 0, and we solve for x. Thus, we have x minus 5 equal to 0, and we have x equals 5. This is now the vertical asymptote, the equation of our vertical asymptote. To determine the horizontal asymptotes, we will look at the degrees of the functions. Now, the degree here, since the numerator is a linear function, while the denominator also is a linear function, then a linear function, the degree is 1. Therefore, the degree of the numerator is equal to the degree of the denominator. If that is the case, we will look for the leading coefficients of the numerator and the leading coefficient of the denominator. Thus, we have the leading coefficient of the numerator is 1, and the leading coefficient of the denominator is also 1. Then we have y is equal to 1 over 1, and we have now the value of our, or the equation of our horizontal asymptote y is equal to 1. That is how we determine the x, y-intercepts, zeros, and asymptotes of our rational functions. More examples in determining the zeros, intercepts, and asymptotes of a rational function in the next video.